Welcome to aminacademy.com. In fluid mechanics, let us discuss about mouthpieces and its classification. A discharge through an orifice may be increased by fitting a sufficient length of a pipe to the outside of the orifice. Such a pipe, which is attached externally to an orifice, is known as external mouthpiece. Here, look at this figure. Here, this is a mouthpiece. This external mouthpiece. Next, a mouthpiece is a short pipe fitted externally or internally to an orifice. The length of the mouthpiece is 2 to 3 times the diameter of the orifice to which it is fitted. That means this length is 2 to 3 times than its diameter of the mouthpieces. Mouthpieces may be classified based on their position, their shape, and the manner in which the mouthpieces discharges. Mouthpieces may be external or internal mouthpieces. An external mouthpiece projects outwards from the tank wall. An internal mouthpiece is fixed so as to project internally. The internal mouthpiece is also called re-entrant or Boda's mouthpiece. Here, this is external. This is external mouthpiece. Now internal mouthpiece, look at figure. Here this is project inverse, that's called it's a internal mouthpiece. Next, convergent mouthpiece. This is a mouthpiece whose area decreases towards its outlet. The inner profile of the mouthpiece almost matches with that of the jet. No sudden enlargement of the flow section occurs, and hence there will be no loss of energy head. That means the mouthpiece almost matches with that of the jet. Hence, the coefficient of velocity and coefficient of contraction are all unity. Hence, the coefficient of discharge is also unity. However, at actual condition, a small loss of head occurs due to friction. The coefficient of discharge is 0.97 to 0.98. Your convergent mouthpiece is a tank. Here, normally if your free hole is there, that water jet flow, then it must here, that means what the jet goes contraction here at vena contracta, that contraction is matches with the cross-sectional area of the mouthpiece reducing gradually. Due to that coefficient of discharge is mostly unity. That means coefficient of discharge is total coefficient of discharge is increased. Only the loss of head loss only due to frictional losses is considered. Therefore, coefficient of discharge mostly in convergent mouthpiece is nearly from 0.97 to 0.98. Next, convergent divergent mouthpieces. We know that in case of cylindrical external mouthpieces, a loss of head occurs due to sudden enlargement that takes place beyond a section inside the vena contracta and the mouthpiece. If this sudden enlargement of the area of flow is prevented, the loss of head is prevented. This condition is achieved in the convergent divergent mouthpieces. Here, now let us discuss about a flow through a external cylindrical mouthpieces. Here, the external, look at this figure. A mouthpiece is a short length of pipe, we know that, two or three times the diameter of it, two times the length about the diameter. That means it is two or three times more than the diameter of the orifice. If this pipe is fitted externally to the orifice, the mouthpiece is called external mouthpiece. Now consider a tank. The water level is height h through the center of the center axis of the mouthpiece. Now let h1 h equal height of liquid, above water surface. Vc is velocity of liquid, at Cc, at section. This is velocity of section Sc at Cc axis, and Ac is area of flow. Area of flow of liquid at vena contracta. At vena contracta. Vena contracta. Next, V1 is velocity of liquid outlet. Velocity of liquid at outlet, and A1 is the area of mouthpiece. Area of mouthpiece at outlet. Now at section 11 at CC and 11, section 11, A flow equation is AC VC equal A1 V1. From that, VC equal A1 V1 by AC, therefore which is V1 over A1 AC over A1. Now AC over A1 is called CC, coefficient of contraction. Now taking coefficient of discharge CD equal to 0.62, we get VC equal V1 by 0.62. Now head loss HL equal Vc minus V1 the square by 2G. Therefore Vc equal V1 by 0.62, which is equal V1 by 0.62 minus V1 the square by 2G, which is equal V1 squared by 2G 1.01 over 0.62 minus 1 the square. Therefore, we can write Vc is, by calculation here, 1 over 0.62 minus 1 whole square is equal 0.375 V1 squared by 2G. Now applying Bernoulli's equation, point A to A and 1 1. Here let this section is 1, the point A here. We'll get PA by rho G plus VA squared by 2G plus ZA equal P1 by rho G plus V1 squared by 2G plus Z1 plus head loss HL, where Z1 ZA equal to Z1 and VA is negligible. At A section A, velocity is negligible. Now we can get it. And also P1 by rho G is atmospheric pressure head. Because this is an open tank, this is equal to 0. Therefore, we can say H height of the water level plus 0 equal 0 plus V1 squared by 2G plus 0.375 V1 squared by 2G. Because it's VC, we have VC is this 0.375 V squared by 2G. We are applying here, and therefore from this we can get H equal 1 point adding V1 squared by 2G plus 0.375 V1 squared by 2G is 1.375 V1 squared by 2G. From this, V1 equal square root of 2GH over 1.375, which is equal 0.855 2GH. Therefore, theoretical velocity. Now, theoretical velocity equal V theoretical. We know that it is 2gh. Therefore, coefficient of velocity is equal actual velocity V actual V theoretical, which is equal 0.855 2gh over 2gh. Both cut, it gives 0.855, which is equal coefficient of velocity CV. Now therefore coefficient of discharge is equal coefficient of contraction, coefficient of velocity is equal, nearly coefficient of contraction is 1 and coefficient of velocity is 0.855, which is equal 0.855. Therefore, the discharge through the mouthpiece will be more than normal orifice. We have done. Please subscribe our YouTube channel.